I saw see, yeah, the thing is, biologists are like, oh yeah, we're doing testing.
Nice.
You need to have a proper discount.
All right. Good afternoon. Any question before we start? All right. Let's continue on.
Empty kegs aren't as heavy. Oh yeah. I remember the first time they had cans and I had to like fill the keg. Oh
Let's
my
continue
God.
on inversion. Sorry, isomer.
It's like, don't mind me struggling.
We learned that we talked about the number synthesis for a given degree of freedom. How many with a different number of links and order of links we can make the kinematic change with that desired degree of freedom. So, for example, for n equals to 1, one of the syntheses that we could find, n equals to 6, c equals to b equals to 4, and c equals to 2. So isomers are kinematic chain with the same number of links and same order of links, but connected differently. So how can I connect these 6 links? I can connect them in this way. 2 terminal links. These 2 terminal links, and I need to have 4 binary, 1, 2, 3, and 4. Another way that I can connect these two are I use 1, 2, 3, 4 binary and 2 terminals. And they have been connected in different ways. So we call them 2 isomers of the kinematic chain. So for this one, we call it what's isomer for this specific isomer, and this one is different. You may think that different isomer for this synthesis, something like this. You might think that we can connect this 4 binary, 1, 2, 3, 4, and 2 terminal links in this way and count it as a different isomer. But this is not a valid isomer because if you look at this part of kinematic chain, I connected this binary link to this one and this one. This part of the kinematic chain is not going to move. This. So since I made the structure in kinematic chain, it cannot be a valid isomer. So we should be careful that just have the valid isomers when you are trying to make a new one. So the only way that I can connect 4 binary and 2 terminal links would be these 2 forms. I cannot connect them in the different ways to make a valid isomer. A structure subchain. I made a structure here, or you might say, what if I have something like this? I have used all 4 binary links, 1, 2, 3, 4, and 2 terminal links, and it's different than this one and this one. But here I have some unused nodes. I didn't use this one, I didn't use this one. So it's again invalid isomer because we should use all nodes and the links. So invalid isomer. So this one is invalid because we didn't use all nodes. This one is invalid because we have made a structure subchain. This part cannot move. This part of the mechanism cannot move. Do you remember that when we had 3 links, 1, 2, 3. This is a structure. This cannot move. So I made something like this here. One part, one link, another link, and another link. So this part cannot move. This part. So for that reason, it's not a valid isomer.
Would it also not count as an isomer if it was preloaded? Like, would you ever be able to have?
No, we cannot.
Okay.
Another example for, I should change to n. N equals to 1, 6 links, b equals to 5, and 1 quaternary. Someone might think that we can connect this in this way. 1 quaternary here, 2 binary links there, and another 3 links connecting here. We have used all nodes for quaternary and the binary links, but this is not a valid isomer because again we made a subchain structure. One of the homework's problem on homework 2 is asking you to, for a given synthesis, I ask you to find some isomers for that one. So it's a good try to find the valid isomers. Alright, let's move on inversion. Inversion. Here I have kinematic chain. Here I have another kinematic chain. Suppose I'm looking at this kinematic chain. I would like to make a mechanism. So I should make one of the links as a frame or ground. So the process of selecting a link as a frame or ground is called inversion. So if I make this link as a ground, the motion of this mechanism is going to be different than when I choose this binary link as a ground. So I'm going to have the 2 different inversions by selecting a different link as a ground. So select the process of selection a link as a frame or ground on a kinematic chain. Kinematic chain, when we don't have any link as a ground, we call it kinematic chain. When we make one link as a ground, we make a mechanism. So if I look at the Watts isomer, I can either make this as a ground. If I do that, I will get something like this. The dashed line is representing the terminal link which has been fixed to the ground. So this is one inversion for the watts. Inversion number 1 for watts ISO. You can fix this link as a ground, but due to the symmetry, you don't get a new inversion. This link, this link, this link, this link, they have symmetry. So another inversion that I can have by fixing one of them. For example, this one. If I fix this as a ground, I will get something like this. This time I fix this one. Again, if I fix this or any other binary links, due to the symmetry between the binary links, I will get the same inversion. So inversion number 2 for watts. So watts isomer has 2 inversions. So if this is link 1, 2, 3, 4, 5, or 6, one of the inversion is coming by fixing either link 1 or 4, the first one. The other one is coming by fixing link 2, 3, 5, or 6. Now I have a mechanism because I have fixed one link. If I want to find the degree of freedom for this, number of links is 6, because we started with the 6 links. 3 times 6 minus 1. How many joints with 1 degree of freedom? All joints in this mechanism are full joint and rotational. 1, 2, 3, 4, 5, 6, 7. Minus 2 times 7. 15 minus 4 is going to give me 1 degree of freedom. Same thing for this one. We didn't change number of links, so it's still number of links is 6. Number of joints 1, 2, 3, 4, 5, 6, 7. The same number of joints. 1 degree of freedom. Good? Now, if I look at the Stephenson 1, link number 1, link number 2, link number 3, link number 4, 5, and 6. I would like to find a different inversion for this. I can start with 10 links of 1. But if you look at 1 and 3, you have symmetry for 1 and 3. So either by fixing link 1 as a ground or fixing link 3 as a ground, you will get the same inversion. So I can fix either this one or link 1 and get the first type of inversion for this one. 4, 3. I will fix 1. This is the terminal link that I chose to be as a ground, and I made this mechanism, moving from kinematic chain to mechanism. So either the second one, 2 or 4, it's going to be the second one, and the last one would be 5 or 6. We will get 2 or 4, 6, 5 or 6. I don't draw them, but we will get the same. Again, the different inversions, they have the same number of links and same number of joints, but the motion would be totally different. So now, let me this is the different inversion for Stephenson. Stephenson meaning 2 terminal links, which is this guy and this one, and 4 binary, 1, 2, 3, 4. And these are 3 different inversions that I have here. Here I fixed this one, 2 or 4. Right here I fixed 5 or 6, which is this one. And here I fixed, I guess, this one. Let's see. By fixing the different links, we can get different isomers, different inversions. And different inversions are going to have a different type of the motion. I didn't change the number of links, I didn't change the size of the links, just picking the different link of the graph. Good? Any question on this? Alright. Let me look at another example for inversion. It's for a slider graph. I have the kinematic chain for the slider crank. One link is this one. One link is this one. Link 3 and link 4 is the slider. So we have 4 links. So I have 4 links. I can fix any of these 4. I will start by fixing this one. It's a slider fixing link 1, link 2, link 3, link 4. Fix link 1. So in this inversion, a slider translates. What's happening if I move this mechanism, this slider is gonna move. It's gonna have translational motion with respect to link 1. Now, the second slider, the second inversion I'm fixing link 2 to select another inversion. Fix. So this link cannot move. What's happening, I'll show you on the video. This slider is going to have complex motion. It's going to have rotational as well as translational. The slider has complex motion. Inversion 1. Inversion number 2. In number 3. I fixed link number 3. If I fix link number 3, link 4 is going to have pure rotation. It cannot move because this link has been fixed, so it cannot, this joint cannot move. So slider has pure rotation, inversion number 2. And last one, the slider is fixed. We fix this one. Fix link 4. Slider is fixed. And it's going to give us inversion number 4. So by fixing different number of links, I will get the different type of the motion for the same isomer. So at the beginning, this one representing this, when a slider is going to have translational motion. It's a typical slider crank that you know. The slider can move along the ground. And this one, we fix this guy. So the slider is going to have complex motion. So it's going to have rotational plus translational. Here it's going to have pure rotation, which is going to be this. And this one, the slider has been fixed. So let me just look at the first one. The slider is going to have translational motion. Second one, we fix this guy. So the slider is going to have rotational motion as well as translational. So it's going to give us complex motion. Here, we fix this guy. The slider cannot have translational motion, but it can rotate about the joints. So it's going to have pure rotational motion. And in last one, the slider is not moving, it's not rotating, it has been fixed. So this link, this is link number 1, it's going to have relative translational motion with respect to slider, and you can see the motion of link 2 and link 3. So 4 inversions, they are going to make the 4 different motions. Any question on this? All right. So let's back slider. This table is gonna just show you based on the number of links and the graph reader, how many isomers, and from those number of isomers, how many mechanisms or how many inversions can we have. With number of links equals to 4, when the graph freedom of 1, we only have one isomer. We cannot connect 4 binary links in different ways. And from these isomers, the only way that you can select a link as a ground, it's going to be, you have symmetry, so you can pick any of the links as a ground to make one mechanism. When it goes to number of links 5, with 2D graph freedom, 5 binary links can be connected only in one way, in this way, and you are going to make only one mechanism by selecting any of these links as a ground. Number 6, the graph freedom is 1, 2 isomers. From those 2 isomers, I can make 3 for this, 2 for this, totally 5 number of mechanisms. Just imagine with 10 number of links, on the graph freedom, we might have 230 different isomers, and out of that we can have more than 800 different mechanisms. So by increasing the number of links, the number of mechanisms increasing exponentially. All right, let's move on the next topic, which is we are going to talk about the Grashof criteria, mechanical advantage, and some other concepts. This topic is about, only 4-bar mechanism. So it's whatever we are covering in this topic, it's valid only for 4-bar. Grashof's law. We start with the Grashof law. Grashof law, it predicts the rotation behavior of a 4-bar mechanism based on the link length. It's gonna predict the rotation behavior of the 4-bar mechanism based on the link length. What do I mean by rotation behavior? You remember that I defined crank, rocker. The crank is a link which can complete 360 degree with respect to the frame. Something like this. This is a 4-bar mechanism. 1, 2, 3, 4. If I run this mechanism, link number 2, this is ground link number 2. Link number 2 can complete 360 with respect to the ground, so it's a crank link. Rocker, any link which cannot complete 360 and it's going to oscillate back and forth. Just look at this one. it cannot complete 360, it can oscillate back and forth between two extreme positions. So we can call rocker. We call this mechanism crank rocker because it has one link as a crank, one link as a rocker. So in this, with the Grashof criteria, what we are gonna do, it's gonna tell us, the Grashof criteria, it's gonna tell us whether or not we are gonna have at least one link which can complete 360-degree rotation with respect to the other links. So it addresses the issue whether or not in a 4-bar mechanism at least one link can rotate
Is this the Grashof law?
it's a Grashof law, yes.
Oh, that addresses the issue?
Yes.
Oh.
Completely with respect to other links. So, for example, this is another 4-bar mechanism. 1 ground, 2, 3, 4. It's these two mechanisms are both are 4-bar mechanisms. This one you can see at least one link, which is this guy, can complete 360 degree with respect to the ground, which is link number 1. It can complete 360. But this one is a 4-bar mechanism still, but if I run it, when it goes to this point, it's gonna lock. When these two line up, when these two line up, it cannot go further. So you like here, you have to switch the direction of rotation and moving in this direction, and when these two links are lined up, again you are gonna lock. So you are gonna lock up between this position and this position. So none of the links can complete 360 degrees with respect to the other. So we call this mechanism non-Grashof mechanism. We call this mechanism Grashof mechanism. So how can the length of links can predict this one? The Grashof law is gonna tell us. So if you have a 4-bar mechanism, 4-bar kinematic chain. First, let's start with kinematic chain. If you look at this kinematic chain, one of the link is gonna be the shortest link. So in this case, this link is the shortest link. I know the shortest link with the S. S label the shortest link. Label L with the longest link. In this example, in this case, longest link is going to be this. And P and Q, the other links. The other two links, it doesn't matter which one is P, which one is Q. we call we label them as this. The Grashof law states that we are gonna have at least one link which can complete 360 degree with respect to the other links if this is valid. S plus L is less than or equal to P plus Q. If the length of shortest link plus the length of longest link is less than or equals to summation of the lengths of the other two links, then there is at least one link which can complete 360 degree with respect to the other links. If this is valid, we say that it's a Grashof mechanism or kinematic chain if we don't have any fixed length. A non-Grashof mechanism if S plus L is greater than P plus Q. If this is valid, then there is no, you cannot find any links which can complete 360 degree with respect to the other link. The book has classified them in class 1, mechanism class 1, mechanism class 2, and mechanism class 3. Class 1. Class 1, S plus L less than, not equals to P plus Q. It's a Grashof mechanism, class 1. Class 2, S plus L greater than P plus Q, non-Grashof mechanism. You don't have any links which can complete 360 degree with respect to the other. And class 3, it's a Grashof mechanism, but it's a special case. It suffers from change point. It suffers. We call it change point. I will explain about that shortly. But still, it's a Grashof mechanism. It's not a non-Grashof. Let me explain about the change point. This mechanism, it's a 4-bar mechanism. 1 link, 2 link, 3, and 4. The shortest link is this one or this one. Doesn't matter which one. In this case, they are the same. And longest link would be this one or this one. So this is a special case for the mechanism. Largest link plus shortest link, as you see, it's going to be the same as the length of this plus this. So we have class number 3 because these two are the same, these two are the same. Now, when it's a Grashof mechanism, meaning that at least one link can complete 360. So I'm going to start from here. I'll come all the way to this point. When it reaches to this point, I cannot predict the motion of this mechanism after that. It can be in this way. This joint can be in the opposite side of this one, or it can go both at the same side of the line. So since I cannot predict the motion of the mechanism, it's suffering from the change point. So again, when it switches to this position, when it wants to pass it, it's a change point. You don't know it's gonna go in this way or it's gonna go in this way. But still, it's a gradual mechanism because this thing and this thing can complete 360 degrees with respect to the other one. So this is the only difference for class 3. Question on this. Alright, let's move on. I'm making the mechanism from this. So I'm making different inversion. Alright. So I have this kinematic chain, shortest link. Shortest link is here, P, Q, and the longest link is gonna be here. I'm gonna make a mechanism, so I should fix one of the links. I will start with the shortest, with this one. With the L, first one. I make the first isomer, first inversion. We are gonna have 4 inversions. S, L, P, Q. And I know that S plus L is less than P plus Q. It's a Grashof mechanism, I know that. So I know that in this inversion, one of the links can have at least 360 rotation with respect to the other one. Second inversion, I'll fix S. I fix S, L is here, P is here, Q is there. Then I fix P. And last one, I fix Q. L, S, P, and Q. Inversion number 1, inversion number 2, inversion number 3, inversion number 4. So I covered all 4 inversions. So I can see that for 1 and 3, for 1 and 3, 1 and 3, where the shortest link is adjacent to the ground. Here in the first inversion, shortest link is adjacent to ground, which is link number longest link. And here the shortest link is adjacent to the link P. So the shortest link is adjacent to the ground. If we have this inversion, we have the mechanism that we are gonna have. It's gonna be crank rocker. One of the links is gonna have, it's gonna be crank, the other one is gonna be rocker. It's kind of this type of the mechanism. 4-bar mechanism, shortest link is this one, ground is this guy, shortest link is adjacent to the ground. So when this mechanism is running, one of the link is cranked because it has been fixed, it has been connected to the ground and it can complete 360 degrees. The other link is rocker because it has been connected to the ground but it cannot complete 360 degrees, it can oscillate. So if this is happening, we are going to have crank rocker. For 2, the shortest link is ground. We are going to have double crank. If this is happening, link P and link L, they are making 360 degrees, both with respect to the ground. So this is going to be the crank, this is going to be the crank because based on the definition, both they have been connected to the ground and they can complete 360 degrees. So it's going to be double crank. And for number 4, shortest link is opposite to the ground. We are going to have a double rocker, which is this. Shortest link is opposite to the ground. So link L and link P cannot complete 360 degrees. They can oscillate, and both they have been connected to the ground. Now, tell me how it's possible that we can have Grashof mechanism, but none of their links of P and L can complete 360 degrees with respect to the ground. How is that possible? The mechanism, the kinematic that I have satisfying the Grashof criteria, meaning at least one link should complete 360 degrees with respect to the other links. But this inversion, when the shortest link is opposite to the ground, it cannot have link P and L. They're going to be rockets, so they're going to oscillate. They cannot complete 360 degrees.
Is it because soon you would have like a straight line between the links and you can't go farther than that?
I mean, what I'm saying that I should have one link at least to complete 360 degrees. So it should be valid for any inversion. Why it's not valid for this one? Any idea? Look at
Links P and L with each other.
pardon?
Links P and L with each other.
The answer is link S is gonna have 360 rotation with respect to P and L.
But they would, yeah, right. Yeah, how would it?
Do you have it?
Let me
actual things.
Give me 1 second. I'll show you. All right, look at this one. So this is the shortest link, the blue one. It's opposite to the ground. It's satisfying the Grashof mechanism. So at least one link should be able to complete 360 with respect to the other links. The blue links with respect to the yellow one or red one can complete 360 degree. At the same time, these two links cannot have pure 360 rotation. They are rockers, but the blue one can complete 360 rotation with respect to the other two. So it's satisfying the Grashof criteria, but it's not a rock. It's not a crank because it has not been connected to the ground. Makes pardon?
You visual of two?
Yeah, yes, sir.
No, but the other word.
Which one? First one or second?
Second.
Double rock crank.
When are we going to have test number one?
In a month. This is a double rocker. These two can complete 360 degrees. Can you see that?
Yeah.
And this one I showed you. It's this one. All right. We continue on right there.